Hi there, my name is Shilpa Koncharla and I'm an engineer on the TensorFlow team. Today, I'll be showing you how to use Keras and TensorFlow to create a video classification model using the conv3D layer. We went over how to load and pre-process video data in my last tutorial. Code from that video and tutorial serve as a prerequisite to some of the concepts I'll be showing you in this video, so I recommend pausing here and checking it out. You can find the link to that video in the description below. Here, I'll outline the differences between a 2D and 3D CNN, how to use the conv3D layer, model architecture, and potential next steps. Okay, let's get started. First, let's cover what a 2D convolutional neural network is. In 2D convolution, you use a two-dimensional filter to perform a convolutional operation, otherwise known as element-wise operations, performed on part of the matrix. This filter, or kernel, is a matrix of the same rank as the input and is multiplied by the input in a convolutional layer. Filters will learn to do things like edge detection or feature detection by looking at shapes and textures. The conv2D layer works well for image processing, and the weights are learned via gradient descent when you train the model. That being said, you may not always want to be working with images. When you work with video data, for example, using the conv3D layer is a suitable option. Let's discuss what a 3D convolutional neural network is and what you can use them for. A 3D CNN uses a three-dimensional filter to perform convolutions. The kernel can slide in three directions, whereas in a 2D CNN, it can slide in two dimensions. This means you can use 3D CNNs to process video data, which you can think of as a cube of frames. You can also use 3D CNNs to process volumetric data, like you might find in an MRI. 2D convolutions perform operations over space, so you can think of a 3D convolution as a volumetric convolution that goes over space and time, or some kind of depth. While 3D CNNs use more parameters than 2D CNNs, they're able to better handle data in which the time or depth matters. In the Keras API, the name for the 3D CNN layer is conv3D. It's important to note that two-dimensional data, such as an image, also has 3D filters within it, namely for a color space such as the RGB planes. Three-dimensional data is different because there is a series of images in a video, otherwise known as frames. The 3D aspect of 3D data comes from the fact that this type of data has spatial and temporal components, outside the number of channels present. So what does a 3D convolutional layer look like in code? Let's take a look at the API and perhaps four arguments you can pass in. The filters parameter represents the dimensionality of the output, or the number of output nodes. The kernel size argument refers to the size of your kernel. This argument can be a tuple of three integers that represent the depth or time, height, and width. It can be a single integer if all of these values are the same. By default, strides will be set to a tuple of 1 by 1 by 1. This specifies the strides the convolution takes along each dimension. A padding value of valid means that there is no padding. If you change this argument to same, this means that there will be a padding with zeros evenly to the left and right and up and down of the input, such that the output has the same height and width dimension as the input. There are more arguments that can be passed in, and if you're curious to see how you can further customize a conv3D layer, please visit the TensorFlow documentation on the conv3D layer. The example I'll use here is a twist on regular 3D CNNs. I wanted to provide you with an example of using a custom layer and show you a trick that you can use to increase the efficiency of your network by reducing the number of parameters in your model. We'll use a 2+1D CNN. In a 2+1D CNN, we start with a spatial convolution, followed by a temporal convolution. A spatial convolution is similar to a 2D convolution shown before, while a temporal convolution is a convolution over one dimension. As the names imply, a spatial convolution will perform the convolution operation over the height and width dimensions, while a temporal convolution will perform the convolution over the time dimension. While a 3D convolution performs the convolution over space and time together, hence it being volumetric, we're just separating them here. A 3D convolutional layer with a kernel size of 3 by 3 by 3 would require a weight matrix with 27 times channel squared entries. When we split a 3D convolution into spatial and temporal aspects, we reduce the amount of parameters used. Instead of having a 3 by 3 by 3 filter, we have a 3 by 3 by 1 plus 1 by 1 by 3 filter, which results in a 9 times channel squared plus 3 times channel squared entries. Now let me show you how to implement a 2+1D CNN by creating a custom Keras layer class. There's a tutorial in the TensorFlow documentation on how to make new layers and models via subclassing, which you can find in the description. We create a Keras sequential object and then add 2 conv3D layers to it. For the kernel size arguments, the dimensional order of the tuple is time, height, and width. For the spatial part, set the time part of the tuple to 1. For the temporal part, set the height and width parts of the tuple to 1. Run through the tutorial to help you understand each component of the 2+1D ResNet that was implemented using the Keras functional API. I really enjoy working with video data, and I hope you do too. As a next step, you could experiment with using more classes from the dataset, or you could work with volumetric data like MRIs, which are really important. I also invite you to share your open source projects relating to video classification down in the comments as well, and perhaps what inspired you to make them. Thanks very much for watching.